O- Okay, we're going to see now the finite element methods and how the computer implements the solution. Because up to now we have seen how we apply Galerkin's method to obtain the individual stiffness matrix of each finite element, but now we want it for the entire region. So what you have in here is in this equation that says that K times phi equals to F. Well, this is the global stiffness matrix, this is the vector of nodal values, and this depends on this debate of constant. The loads have a bearing on what that constant is. So the question is, find the solution. If K is found as in chapter, so in here we will have to produce individual K's. So let's say that we have a simple 2D finite element as you see on the picture, and here we have 4 elements and 6 nodes. Yeah, based on the derivation we did for proving Galerkin's application, Galerkin's method, we concluded that the phi of the finite element, what I'm saying, phi of on each node, phi sub I, phi sub j, phi sub k, so 1, 2, 3, and 4, and so on. We will do it with the properties and with the coordinates. Okay, so you have like I said, 4 elements, 6 nodes. Yeah. Okay. So the bottom line is that if we apply the residual equations like Galerkin wants us to do, we will end up with a linear combination of these shape functions or weighting factors and the nodal values. That's where we're going after this whole thing. Fine. Another element method, how we implement on the computer. So you see in here you have the individual stiffness matrix K sub 3, but if you put using the same notation, see, using the same notation, and we have these matrices. What I'm trying to say is that if you do case of 3, it will be in the finite element model in different parts of the global stiffness matrix, following the coefficients. Now, what's happening here? We need to talk about the system of linear equations that are used to find the solution. Okay, that's what we were doing a moment ago, and now we are at the point of finding out how in the world the computer does the calculations. So, given that problem, global stiffness matrix K, times the vector of nodal values. In here you see this is K stiffness and vector of nodal values equals to vector of loads. Okay, now in here is we're gonna go do something very interesting. Okay, when you generate this matrix, if at all possible you could have it like this, that would be great. And the shorter this bandwidth is the measure of how many elements are filled in the matrix. But if you have this yellow fringe as small as possible, then the computer the speed will increase tremendously to find the solution. So we have some requirements on how that will happen. That K is a symmetrical matrix, and also property is that it should be positive definite. The characteristics of K, of this function, are used to reduce storage space and all other modifications that we can do to do this. So in this case we have problems in solid mechanics. Some displacement is specified to eliminate rigid body degrees of freedom. So if you have the original system as is in here, if you have it in here, and you make any modification to it, the modification must give the same answer, and the size of K and F should not change. Okay, so in here what I wanted to say, I'll just remind you very briefly how this works. What I'm trying to say is that in here, this one, if we multiply both sides by the inverse, okay, so this becomes the identity matrix. What did I just do with here? This was F, but this has to be multiplied by the inverse of K in this case. So if this is the identity matrix times the vector phi equals to the inverse of n, so we have minus in here, okay, so in here you have the nodal values are the inverse of K times the vector phi, like this. And this is what we apply to all this Okay, any questions about this? I think what I would say is that this happens when we are in what part of the pattern tab, where when this is happening. Where are we on the pattern tab for doing these calculations? On the analysis. Okay, and that's the analysis tab. We generate the matrix and then we submit the matrix as well.